Hello, everybody. This is Nafrit Sekho, and I welcome you on this platform, The Layers of Life Sciences, where we are discussing various aspects of life sciences in quite depth and detail, layer by layer. The objective is not just to help you in your graduation, post graduation, and competitive exams, including CSIR NET, but also to have a discussion about the life processes happening around us. We have started with biochemistry, and in that we have started with the discussion of structure of carbohydrates. In first two videos, which is biochemistry 1 and biochemistry 2, we discussed the linear structures of aldoses and ketoses in quite detail. Both aldoses and ketoses are the different forms of monosaccharides, which are the building blocks of larger macromolecules, the carbohydrates. In the third video, which is biochemistry 3, we discussed that how the linear structure of aldoses undergoes a twist to form the cyclic structure of aldoses. I hope you must have watched this video before you proceed with this next video, where we are going to discuss the cyclic structure of ketoses. First of all, we will study how this cyclization happens. This cyclization also happens when the linear structure of ketoses undergoes a twist under the effect of a chemical reaction between here ketone and an alcohol. So which means here also the twist in the structure involves a backstory. This backstory again lies in the realm of chemistry. So to understand once again the cyclization, we need to go to the realm of chemistry. So let's start with that. So first of all, let me introduce you to the characters of this story and how these characters are differing from the story which was in the backdrop of the cyclization of aldoses. So the first main character in this story are the ketones. So what is a ketone? As we discussed in the first lecture, that is biochemistry 1, that what are ketones? They are just formed of the chains of carbons. So there are two terminal carbons over here and three are interstitial carbons. Now, any of these interstitial carbons, whenever decide to form a double bond with an oxygen atom, then a ketone is formed. So now over here, if this carbon has chosen to form a bond with an oxygen atom, now it has no ability to form any other bond, while rest of the carbon atoms will fulfill their tetravalencies with the help of hydrogens. So over here, if you look at this much group, as we discussed in the last video, where we were discussing the main characters of the story involved in the cyclization of aldoses, we said that this is again alkane in which one of the hydrogen is lacking. So it means this much group is an alkyl group, right? This group over here is an alkyl group. Now, this alkyl group is joined with a carbonyl group. And again, this group over here is again an alkyl group, right? So here on the both sides of the carbonyl group, there is an alkyl group. So if we want to write the generalized form, then be this propyl group Br1, and which is further bonded with the carbonyl group, and then this one Br2, right? So this is the ketone. Now, it is very important to point out over here that how it is different from aldehyde. In aldehyde, in place of this alkyl group, first of all, aldehyde is formed when the terminal carbon decides to get involved in the formation of this carbonyl group. For example, let's take the same kind of group of involving 5 carbons. Now over here, This carbon decides to form the bond, or this carbon decides to form the bond, double bond oxygen, right? So rest all the carbons will fulfill their valencies. Now, this carbon will also fulfill its fourth valency with the help of hydrogen. So if you look at this, till this group, this is alkyl group, which can be referred as R. Then comes the carbonyl group. Now, this carbonyl group on the other side is bonded just with hydrogen. Here it is bonded with another alkyl group, whole of an alkyl group, just because here the interstitial carbon is choosing to get involved in the formation of carbonyl group. Here it was the terminal carbon which just decided to go with the double bond oxygen. So therefore over here, that is the difference. That is the only difference. Over here it is the H, and this is the difference which will get reflected even after the cyclization of the ketoses as well as aldoses. Now I hope this difference is clear. Now the second character is just as it was there in the case of cyclization of aldoses. The second character in the backstory is again the alcohol. Nothing but alcohol. So we just did over there. What is alcohol? Alcohol is again an alkyl group, any alkyl group, right? CH3, CH2, which is bonded with a single bond with an oxygen atom. So now oxygen being divalent needs to form another bond, and when it forms that another bond with the hydrogen, then this group over here is called hydroxyl group, and the presence of hydroxyl group in any molecule gives it alcoholic character. So this forms an alcohol. But whenever this oxygen, which is bonded over here, let's take another example. So if it is CH2 only, and this alkyl group is bonded with oxygen, but this again this oxygen binds with another carbon, and which may be simply methyl. So this is basically, this is ROH group, this is R, this is the general formula of alcohol, and this is ROR basically, right? ROR group, and this is called ether, which we actually discussed in detail in the last video as well. These are the general forms. This is a ketone, like this is the ketone, general formula for ketone, and this is the general formula for alcohol, and this is the general formula for ether. Now the characters are well introduced. Let's see how these characters act in the story. So what happens is that this alcohol over here, whenever interacts with any ketone, this alcohol leads to the shift of the electrons of one of the double bonds in carbonyl group towards oxygen. This shift of electrons is due to the electromeric effect of this alcohol over here. As defined in the earlier video, the electromeric effect is the shifting of the electrons of one of the bonds of a double bond towards the more electronegative atom in presence of any agent is called electromeric effect. That shift is called electromeric effect. So agent over here is alcohol. So this alcohol leads to the shift of electrons of one of the bonds. One bond remains intact while just both the electrons of other bond shift towards oxygen. This leads to the negative charge on oxygen and a positive charge on carbon. So here the first action of two things is completed. Now, second step. After this alcohol undergoes a Heterolytic cleavage. So heterolytic cleavage happens in the bond which is there between this hydrogen and oxygen. This hydrogen over here and this oxygen over here. So there is a bond between them, which I have expanded over here. So when this bond breaks, then again, both the electrons go towards oxygen and this oxygen becomes negative. And then we are left with a free hydrogen ion, or we can say hydronium ion, which is positive. All the positive species in chemistry are basically the electrophiles, means they get attracted towards the negative charge. And the negatively charged species are always the nucleophiles. They are always the nucleophiles, while others are the electrophile. So actually, after the heterolytic cleavage, here a nucleophile, this much part, a nucleophile and an electrophile is created. Now this nucleophile, that is OR negative, conducts a nucleophilic attack on this positive carbon. Nucleophile being negative conducts a nucleophilic attack on this positive carbon and succeeds in forming a bond with carbon. So this OR3 gets bonded with carbon over here. Now, then this positive H, that is H positive, which is basically electrophile, gets attracted towards this O negative and forms the bond with it, forming the OH group. Now, this molecule which has been formed where a carbon is bonded with 4 different groups, here alkyl 1, alkyl 2, and over here hydroxyl group, and basically over here it is bonded with an ether group. So this molecule where such things are happening, this molecule is called hemiketal. Now, that's why this carbon is also called hemiketal carbon. This hemiketal carbon has been derived from this carbon involved in the carbonyl bonding, where it was achiral, which means it was not chiral over there because 2 of its valencies were being fulfilled by the single oxygen molecule. But over here, all its valencies are being fulfilled by 4 different groups. So this carbon has now become chiral. This is newly created chiral carbon, which is also called hemiketal carbon. And when it will be involved in the cyclic structure, it will be also called anomeric carbon. So the basic difference over here, hemiketal has been formed. In the earlier video where we did the cyclization of aldoses, there the molecule which was formed was hemiacetal. And the only difference over there is that instead of this R2 over here, there was H. So over there, this carbon had OR on one side, R1 on R on another side, and on other 2 sides, it was bonded with hydroxyl group and the hydrogen group if it was hemiacetal. But now, as if it is hemiketal, no H group, right? So these are the major differences in the basic chemical reaction. So now, as the backstory is clear, let's see how this backstory leads to the cyclization. Now, this backstory leads to the cyclization when this same reaction, instead of occurring between 2 different molecules, here there were 2 different molecules, right? So this reaction was basically intermolecular. But when both these groups, means carbonyl group as well as the hydroxyl group, carbonyl group on the central carbon, right, and the hydroxyl group will coexist within the same molecule, then also they will react in the similar manner. At that time, it will be an intramolecular reaction. So whenever these 2 groups, like ketonic group as well as alcoholic group, interact within the same molecule, then the cyclization takes place. Let's see how. this is a ketohexose. Why it is a ketohexose? Because there is carbonyl group present on an interstitial carbon, and rest all the carbons are fulfilling at least one of their valencies with the help of hydroxyl group. That's why it is polyhydroxyketone, and generally the polyhydroxyketone is called ketoses, right? So this is a ketose, and because this ketose is composed of 6 carbons, it means it is a ketohexose. Now, what happens over here? That this carbon number 2 is bearing the carbonyl group. Now, this hydroxyl group present on carbon number 5 or this hydroxyl group present on carbon number 6 may interact with this carbonyl group on carbon number 2 and lead to the electromeric effect in that, which means the electrons of one of the double bonds will shift towards the oxygen. And when they will shift towards the oxygen, oxygen will become negative and it will become positive. Once such kind of charges are created on the carbonyl group, then this group over here also will get broken, or we can say the cleavage of this bond will also happen with a negative charge on the oxygen and a positive charge on hydrogen ion. So this negative oxygen will conduct a nucleophilic attack on this positive carbon and will succeed in forming the bond. Let's see how this happens in the next slide. So actually, this structure is nothing but the same, that linear structure, here it in a proper form, right? So what happens is, so you can see this is carbon number 1 to carbon number 1, carbon number 2 is bonded with its carbonyl group. And then with the carbon number 2, carbon number 3 with its hydrogen and hydroxyl, with carbon number 3, carbon number 4 is bonded, and carbon number 5 is bonded. Now on this hydroxyl on carbon number 5 will actually act as an agent, and when it will act as an agent, it will lead to the electromeric effect on this carbon number 2, which will lead to the shift of the electrons with the creation of negative charge on oxygen and a positive charge on carbon. Now, once this creation is done, the heterolytic cleavage will be there between the oxygen and hydrogen, and as both the electrons involved in the bond will get shifted on towards oxygen, and this hydrogen will become H positive, right? It will lose the only electron which was actually there with it. So now this oxygen over here will conduct a nucleophilic attack on this carbon and will succeed in forming the bond, as it was COR. This is COR bond, which you actually noticed in the structure number 3 in the first basic slide. So now this bond is formed. Once this bond is formed, actually the cyclic structure has, or the ring formation is completed. So cyclic structure has been formed. Now, after that, this hydrogen will get bonded with over here. So there, this bond is no more there. So there is a single bond only. So this carbon over here is bonded with this oxygen, which is further bonded with carbon number 5, and over here this is bonded with this R and this CH2OH, which we can consider as R, and on this side it is bonded with OH, and on this side this is R2. This can be considered as R1, this can be considered as R2. So this is again that hemiketal carbon which we discussed in the first slide. This carbon is now a hemiketal, newly created chiral carbon basically. So let's see what the result is. The result will be, we can see the result on the slide over here. So this is the carbon number 2, which is bonding with hydroxyl group on one side, alkyl group R1 on another side, R2 on other side, and OR3 on the fourth side. So this is newly created ketyl carbon. Now, this we can see, this is the structure. This is the basic structure. Now, as we know that this is the newly created chiral carbon, so it means wherever the chirality is there, stereoisomerism is there, and wherever stereoisomerism is there, it means there must be the stereoisomer. So over here, as there is only one newly created carbon, by the formula of finding the stereoisomers, that is 2 raised to the power n means the number of chiral carbons, right? So only one newly created chiral carbon is there. So 2 stereoisomers are possible. So one of the stereoisomer is beta and another one will be alpha. So beta is one which you can see right now whenever the hydroxyl group is directed upwards and R1 group is directed downwards, then this is basically the beta stereoisomer. While if the opposite happens as in this case, so over here hydroxyl group is directing downwards, and our CH2 OH group, which can be considered as R1, is directing upwards, like both C6 and C1 both directing upwards, means this stereoisomer is alpha. So this is alpha. So these are the 2 stereoisomers which are created. So this was actually the mechanism. Now let's discuss about all the possibilities and how we can create the cyclic structure if we actually know the linear structure. So we actually, after learning the codes, we must be pro with the linear structures of all the aldoses and ketoses. So let's see how we can do that. Now, as we have learned that how the linear ketoses can be converted into or translated into the ring forms, and what is the mechanism behind that, now it is very important for us to learn that how we can translate the linear structures of ketoses into the ring structures, or we can say the cyclic structures. Now, if you have learned the codes which were mentioned in the video number 2, that is Biochemistry 2, you must have become pro with the linear structures. Now, if you know the linear structures, you need not to learn the ring structures, or we can say cyclic structures of all these monosaccharides. You can easily create the ring structures, and which is actually the better way, because otherwise confusions will always be there, and we can certainly go wrong if we try to learn the structures rather than learning how those structures are formed. So before we learn how to translate these linear structures into the cyclic structures, few things should be clear in our mind. Number one thing, that apart from the ketoses, which are composed of 5 carbons, which are ketopentoses, or which are composed of 6 carbons, which are ketohexoses, none of the other ketoses can undergo cyclization. They cannot form the cyclic structures. They exist only in the linear forms. 2 kind of ketoses which can undergo cyclization are ketopentoses and ketohexoses. So first one is the ketopentose, and second one is the ketohexose. So the structure which is already drawn over here, you can see that this is basically a ketohexose because it is composed of 6 carbons. So over here, there are 2 possibilities. The 2 possibilities are that this hydroxyl group on carbon number 5 may interact with this carbonyl group on carbon number 2. So the first possible interaction is between this hydroxyl group on carbon number 5 and this carbonyl group on carbon number 2. So if this is happening, that there is the interaction between carbon number 2 and carbon number 5, right? Now, what is the second option? Second option is that this hydroxyl group on carbon number 6 may interact with this carbonyl group on carbon number 2. So second possible interaction is between carbon number 2 and carbon number 6. If the interaction is between carbon number 2 and carbon number 5, it means 4 carbons are involved. While when their interaction is between carbon number 2 and carbon number 6, then in that case, 5 carbons will be involved in the ring formation, right? All these 5 carbons will be involved in the ring formation. Like this. Now, we have learned in the last video that if 4 carbons are involved, then the ring which is formed is always pentagonal. 4 plus 1, 5-angled pentagonal. But if 5 carbons are involved, then the ring which is formed is 5 plus 1, 6-angled hexagonal. So whenever the pentagonal ring is formed during the cyclization of any of the ketoses or aldoses, then that pentagonal ring is called furanose ring. So pentagonal ring will always be called furanose ring. And if hexagonal ring is formed, then that ring is called pyranose ring. First of all, let's see how furanose ring is formed. So furanose ring will be formed when this hydroxyl group on this carbon number 5 will act on this carbonyl group on carbon number 2 and lead to the electromeric effect on the pentagonal ring. So this oxygen of the hydroxyl group of carbon number 5 that will conduct the nucleophilic attack. So that attacking oxygen is always placed on the top. Oxygen on one side will be bonded with carbon number 5, right? And on the other side, it will form a new bond with carbon number 2. So on this side, this will be carbon number 2 with which it will be bonded. Right now, first of all, let's see what is the situation of carbon number 2. Carbon number 2 on one side is bonded with this oxygen over here, that is the one bond, while on the other end it is bonded with carbon number 1. So this carbon number 1 will show over here. Now this is the carbon number 1. So carbon number 1, carbon number 2. So on the third side, like third bond is been formed with carbon number 3. So this carbon number 3 will be over here. This is carbon number 3. This carbon number 3 is further bonded with carbon number 4. And this carbon number 4 is bonded with carbon number 5. This carbon number 5 is bonded with carbon number 6. Over here, for this carbon number 2, which is basically the hemiketal carbon, newly created chiral carbon. And this is first bond, this is the second bond, third bond, and the fourth bond will be formed with this oxygen over here, which now is further bonded with hydrogen. So this OH group will come over here. Right? Now, this is done. Now let's check the carbon number 5 on the other end. Carbon number 5 on one end is bonded with CH2OH. On the other end, it was bonded to its own oxygen, which is now further bonded to carbon number 2 as well. On the other side, it is bonded with carbon number 5. So the only group which remains to be mentioned is hydrogen, just one hydrogen. Now, both these carbons are done. Now we are left with carbon number 3 and 4. We know that this carbon number 3 and 4 both are the chiral carbons in the linear structure. It means the configuration around them matters, right? Configuration of H and OH around them matters. So here there is a rule. The rule is that all the groups which are mentioned on the left-hand side of the carbon chain should be directing upwards. So once again, all the groups which are mentioned on the left-hand side of the carbon skeleton in the ring structure, they should be pointing upwards. And all the groups which are mentioned on the right-hand side should be mentioned downwards, should be directing downwards. So let's see. Let's see what is the scenario on carbon number 3. On carbon number 3, OH is on the left-hand side. So on the carbon number 3, this OH should be directing upwards. So it should be directing upwards, OH. And H is on the right-hand side, so it should be directing downwards. So now we come to group number, carbon number 4. On carbon number 4, this is carbon number 4. H is on the left-hand side, so it should be directing upwards, while OH over here is on the right-hand side, so it should be directing downwards. So this is the structure of fructose. How do I know that this is the fructose? From the linear structure. I know this is ketohexose, right? Now, which ketohexose? It is D-ketohexose, because the orientation of hydroxyl group on the carbon, chiral carbon, which is farthest from the carbonyl group, it is directed towards the right-hand side. So this form is certainly D form. Now, what is the formula of that D form? It is 45. So for ketohexoses, D-ketohexose, for which the formula is 45, is always fructose. So this can be translated into the furanose ring. This is again the furanose ring. So in this manner. So we can easily translate any of the linear structures into the cyclic structures in this way. So the ring which is formed is the furanose ring. Which furanose? Because it has been derived from D-fructose, so it is D-fructofuranose. D-fructofuranose. Which form? Ring is in the which form? So OH over here is directed downwards. It means this is the alpha D-fructofuranose. So this is its proper naming. Another structure which was possible, if this OH would have been directing upwards, then this form would have been known as beta D fructofuranose, in that case, right? Furanose. So this is the structure. Now, if instead of this hydroxyl group on carbon number 5, this hydroxyl group on carbon number 6 acts on this carbon number 2, then certainly hexagonal ring will be formed. So let's form that hexagonal skeleton first of all. Then we need to fill that skeleton according to the rules. And all these structures which I'm drawing right now, they are Haworth projection formulas. Their 3D aspect we will understand in coming videos. So this is the hexagonal structure. Let's place this oxygen, which is making the nucleophilic attack on this carbon and is joining it. It will always be placed on this side. Right? Now, this oxygen on one hand is bonded with the carbon number 6. So this carbon number 6 is bonded with another carbon, which is carbon number 5. Then carbon number 5 is bonded with carbon number 4. Then this carbon number 4 is bonded with carbon number 3. And this carbon number 3 is bonded with, and this oxygen is also bonded with carbon number 2. And this carbon number 2 is further bonded with the carbon number 1. Carbon number 1 has the groups CH2OH. This will remain as it is. While another group is the newly formed OH, which will be joining this carbon number 2, right? Now, done. Now we need to go to carbon number 6. On carbon number 6, this O is already there. H has joined over here. Now it is left with just 2 H's. So 2 H's. Now carbon number 5, 4 and 3. are basically the chiral carbons. So configurations around them matter, but the rule remains same. Whatever is placed on the left hand side of the chain, it will be drawn pointing upwards, and whatever is directed on the right hand side, it should be drawn directing downwards. So on carbon number 3, on the left hand side, it is OH, right? Here it is OH, and then on carbon number 5 it is H. 4 it is H, and on carbon number 5 also it is H on the left hand side. Now right hand side groups should be pointing downwards. So on carbon number 3 it is H, on carbon number 4 it is OH, and on carbon number 5 it is again OH. So again 45. This is again the structure of fructose, right? Cyclic structure of fructose, but this is the pyranose structure. So therefore its name will be pyranose ring. Which pyranose? It has been formed from fructose, right? So D-fructo. And now which form is this? Again, OH is pointing downwards. So this, the drawn form is basically the alpha D-fructo. And another possible form is beta D-fructo. Beta D-fructopyranose. So for any ketohexose, we have learned with this example of fructose that 5 forms are possible. First form is this linear form over here, this linear form, then 2 furanose forms, and then 2 pyranose forms. These 5 forms are possible. Generally, few of them are dominating and others just exist in traces. In the case of fructose, the most abundant form is beta D-fructopyranose, basically. And second abundant is beta D-fructofuranose. These 2 forms are most abundant. 70% is this and 30% is this, while this linear form and these alpha forms are just in traces. But this is just in the case of fructose. In the case of other ketohexoses, the abundance may be different. So this is about the ketohexose. Now let's come to the ketopentose. First of all, let's draw any ketopentose. Any ketopentose, like for example, xylulose. We can draw xylulose, right? So if we try to draw that, we are drawing ketopentose, so it means it will be composed of 5 carbons. So let's draw the Fisher projection formula of ketopentose. So the second carbon will have the carbonyl group according to the conventions of Fisher projection formula. Now this, in that case, these both the terminal carbons will be bearing 2 hydrogens and 1 hydroxyl. Right, 2 hydrogens and 1 hydroxyl, and the valencies of carbon number 2 are already fulfilled. Now these are the 2 chiral carbons. We need to be very careful about their configuration. So the code for xylulose is 4. It means on carbon number 4, OH needs to be on the right hand side. We are actually drawing the D-xylulose. So the 4th carbon is this one. So over here, OH is on the right hand side. If that is the code, it means on the carbon number 3, OH is on the left hand side. On the alternative sides, we can draw the H. So this is how we can draw the structure of xylulose. Now, we need to draw its ring structure. But before we do that, we just need to know that the distance between this carbon number 4 and this carbon number 2 is not appropriate for the nucleophilic attack. That's why in case of ketopentoses, the always and always this hydroxyl group on carbon number 5 interacts with this carbon on carbon number 2. It is never the carbon number 4. It means always and always there will be just 4 carbons which will be involved. So the only possible interaction over here is carbon number 2 and carbon number 5. So if that is the case, it means just 4 carbons will be involved in the ring formation, which means always and always a pentagonal structure will be formed. It means only furanose rings are possible. Only the furanose ring structures are possible. So if we try to translate this linear structure into the ring structure, rules are same. So we can draw the skeleton over here. So this is, and oxygen will be placed at the top. This oxygen, which is making the nucleophilic attack. Now, this oxygen on one side is bonded with this carbon number 2, so which is placed over here, right? And it is a hemiketal carbon. Carbon number 2 over here is hemiketal carbon. And on other side, it is bonded with the carbon number 5. So we need to write the carbon number 5 over here. This carbon number 2 is further bonded with carbon number 1 with its CH2OH group, while on the fourth side, it is bonded with this oxygen, which is now further bonding with hydrogen from here. So there is OH group over here. While if we see carbon number 5 on one side, it is bonded with this oxygen here, right? And on other side, it is bonding with carbon number 4. And so rest 2 bonds are just with hydrogen. So just hydrogens, no problem. Now, we are left with the chiral carbons. Again, the configuration rule is same. Whatever is on the left-hand side of the carbon skeleton should be pointing upwards. So over here on carbon number 3, here there is carbon number 3 and here there is carbon number 4. On carbon number 3, OH should be pointing upwards, and carbon number 4, it should be pointing upwards. And over here on carbon number 3, H should be downwards. Over here, OH should be downwards. So this is the cyclic structure of cellulose, which is basically furanose form, right? So we will start with the word root furanose in naming, right? Furanose, that is the word root. Now, which form has been converted into furanose? It is D-xylulose. So we will use D-xylulo, right? And which form has been created? Again, OH is directed downwards, so alpha form has been formed. This OH may direct upwards, then beta D-xylulofuranose may be created. So these 2 ring forms and 1 this linear form. So in case of ketopentoses, only 3 structures are possible. So which is quite a different case when we compare with ketohexose or aldopentose or aldohexose, right? In all these 3 groups, 5 forms are possible, but in ketopentose only these 3 forms are possible, and this is how we can translate the linear structures into the ring structures. Now, I hope there should be no problem and there should be no apprehension regarding the structures of monosaccharides. So the only important thing which we need to do is we should be very well acquainted with the linear structures of the monosaccharides, and the method how to do that I have explained in Biochemistry 2. And please watch it and learn those structures if we want to be very, very clear and sorted about the structures. And then further, when we will be doing the metabolism, we need to be sorted about the reactions, their reactions with other things. So it is very important that we should be very, very pro with the structures. So till this point, we have been discussing different forms of monosaccharides, be it aldopentoses, aldohexoses, ketopentoses, or ketohexoses. So now, how do we know that all these exist, and what is the major difference in their behavior? Major difference is the difference in their optical activity. Now, what is this optical activity? We referred to this word when we were doing stereoisomerism, maybe in video Biochemistry 2. So What is this optical activity? Optical activity is the ability of any molecule to rotate the plane polarized light. Now, another term, what is this plane polarized light? What happens is that we know that light is the electromagnetic radiation. So, which means that when the electric field and the magnetic field both interact with one another at the planes perpendicular to each other, then electromagnetic radiations are created. For example, this is the electric field and this is the magnetic field. Now, if these two will interact with one another at a plane perpendicular to each other, then resultant electromagnetic radiation will be created. If this is the x-axis and this is the y-axis over here, then this resultant electromagnetic radiation will be along the z-axis. It is again perpendicular to both x and y. We are referring to just part of that electromagnetic radiation spectrum, which is the light, just a small part of that. So we are concerned with light because we need to learn about plane polarized light. What is this plane polarized light, which is used to measure the optical activity of these molecules and in turn the difference in their physical behavior. Suppose this is the plane of propagation of that resultant light to every possible perpendicular direction the electric field is oriented. So if this is the case, this is the propagation of the light, direction of then the electric field, when it explores all the possible perpendicular planes to that plane of propagation, then that kind of light is called unpolarized light. This light is the unpolarized light. The light which is coming from any source of light is unpolarized only. Now, this light can be polarized by using a polarizer. This polarizer will just allow only those electric radiations which are parallel to its orientation. So once this light will pass through it, then this will be the case. This electric field is in just one plane. Right here, it was going to all the possible planes. Here, this electric field is just exploring or is just restricted to one plane. Now, when this electric field is restricted to one plane, perpendicular to the plane of propagation of light, then that light is called polarized light. So, for example, this is the plane which was chosen. Now, if this polarized light is passed through any medium, right, from any medium of suppose beta D glucopyranose, right? So any medium or any solution, right? If it is passed through any solution, and then we again observe, then it may remain same, like it may not be tilted, then it means this solution was optically inactive. But if this rotates, for example, this was the original form, for example, this was its original plane, right, before passing through now ultimately after passing through the solution, it rotates towards at a certain angle, right, towards right. It means this first of all, it means this solution is optically active. First point. Then how it is active? This solution is optically active and it is dextro-rotatory. Now we will measure this angle, that how much rotation has happened. That measure will tell us the degree of optical activity. This angle will be measured in degrees. So we will know the degree of optical activity, which will be mentioned along with the sign, which can be negative or positive. So if it is dextro-rotatory, then the sign in front of that degree, for example, let it be 20 degrees. So here it will be plus 20 degrees, which means that the solution through which this plane polarized light has been passed, it is able to rotate that light by 20 degrees towards right, and that medium is actually optically active. Now, if this light, after passing through this, then if this was the original, then it may rotate towards left hand side like this, right? So if it is rotating towards left hand side, it means it is levorotatory, and we will again measure the angle by which the rotation has taken place. That will be the measure of the optical activity of this material, and we will have to write just for example 30 degrees. So now in front of that we will have to write minus 30 degrees. The minus sign over here will denote that the rotation of plane polarized light has taken towards the left hand side, and that's why this solution is levorotatory. This is all about the optical activity. When this optical activity is measured up for a certain amount of solution of that material at a particular temperature, then we call it as the specific optical activity, which is just denoted by this alpha within the brackets. Now, what happens is that when I dissolve beta D glucopyranose, right, and try to measure its optical activity, I get to know that it is able to rotate the plane polarized light by 19 degrees towards right. But when I dissolve alpha D glucopyranose in water and try to analyze its optical activity, then I realize that it is able to rotate the plane polarized light by 112 degrees towards right. It means their physical properties are very different, and this I should be doing immediately after dissolving. Now, I keep both the solutions for a while. I keep both the solutions. So if both the solution, this solution, which is alpha form of glucopyranose, it has the optical activity. It has optical activity of plus 112 degrees, and there is another form which is the beta form. It has the optical activity of 19 degrees, just 19 degrees. Both are rotating the light towards the right hand side only. But now I am keeping it still for a while. Now, after a while, maybe 2-3 hours, when I try to analyze the optical activity again for this alpha, I realize that it has reduced to plus 52 degrees, while the optical activity of beta form has increased to plus 52 degrees. Okay, so it is like after a while, both the solutions just became same, right? No difference at all. Now, what has happened? What has happened? Why so? The reason behind this is that both the structures are not stiff and strict in their behavior. They are open to conversions, like beta form is open to getting converted into the linear form and to the alpha form. Right? So same is the case with the alpha form. Alpha form is open to get converted into linear form as well as the beta form. So what happens if we say this alpha form, when it is dissolved, everything is alpha form. Now this alpha form, when we just keep it for a while, during that time, this alpha form starts getting converted into beta form until or unless alpha form itself is just 1/3 of the solution and 2/3 of that solution becomes the beta form. So and now after a while in this part, alpha and beta forms both exist, which leads to the optical activity of plus 52 degree. Same thing happens in this beta form. This beta form, initially everything is beta form or beta pyranose. Now this beta form starts getting converted into alpha form. Once 1/3 of the solution becomes the alpha form and 2/3 remains beta form, then no further conversion takes place. Now, this solution is the resultant solution. Again, you will notice that both here also alpha is 1/3, here is also alpha is 1/3 and beta is 2/3. So they are actually the same. So this solution where 1/3 of the solution is alpha and 2/3 of the solution is beta, is called equilibrium mixture. So this is an equilibrium is reached, right, depending upon the stability of the two forms. So whenever you will rest the solution of a particular form for a while, then the other form will start emerging. The first form will start getting converted into the second form, and a resultant equilibrium mixture will be created, in which 1/3 of the mixture will be alpha, 2/3 will be beta, and rest less than 1% will be the linear structure. And yes, Furano's forms will also be there, which because they are possible, but they will be like very, 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 very negligible, and they will be that negligible that they would not affect the resultant observed optical activity. So this is the equilibrium mixture. So now this process of conversion of alpha form to beta form to alpha form, this process is called mutarotation. One thing which we learned, that these forms are not very stiff and strict in their behavior, that they are open to getting converted into the other forms as well. This thing leads to the beta rotation. I say goodbye over here. If you have any questions, if you have any doubts, I'm happy to discuss. See you next time.